any case, if I go too far in either direction, if I'm going too fast and you're not really sure what I'm saying, or if I'm going too slow and telling you all things that you already know, then just please don't hesitate to let me know. Also, if you have any questions, feel welcome to ask. I probably won't see the chat, but you can just unmute yourselves and talk, and I think this should be fine. We're not such a large group that this would cause a problem. Okay, so today I'm going to talk about algebraic structures on automorphic functions, and let me begin to explain what I mean by that. So first of all, just let's give the words of introduction that we must all give whenever we talk about L functions. So L functions are very important objects. They're very useful in many branches of mathematics. Usually the idea is that you have L functions coming from different kinds of objects, representation theory, number theory, etc. And when these two L functions are equal, then you get some kind of deep connection. In this talk, we're not going to be talking about any of that at all, any of that Langlands stuff. We're only going to be discussing what are called automorphic L functions that come from representation theory. Specifically, our focus will be on GL2, on just the general linear group of order 2. That will be sufficient for us in this talk. So what happens when you have, so let's say that I have an automorphic representation of GL2 and I want to associate an L function to it, then there is this procedure that allows me to do so. There's some kind of recipe. Basically, there is some formula that takes some kind of data, maybe vectors in my representation, test functions, all sorts of other assorted data, and constructs something called a zeta integral out of it, through some integral formula. This integral, when you do this procedure, you don't get just one integral, you get a whole family of them. And then there is some mysterious procedure usually called the GCD procedure that takes this family of zeta integrals and turns it in and selects just one representative out of this family, which is called the L function. Now, even just when we look at GL2, which is the basically maybe the simplest case, there's not just one way to produce these zeta integrals, but there are actually two very different kinds of formula. So for probably there are more, but these are the main ones that people usually talk about. So the first one is Godement-Jacquet zeta integrals. They take pairs of vectors from the representation and some test functions, and Jacquet-Langlands zeta integrals, which just uses a single vector from the representation. So you have this kind of zeta integrals that are very, very different. They use very different data. And somehow the L function that they end up with is the same L function. It's the same L function that we associate to our automorphic representation. Now, the focus on this talk is going to be basically a philosophical idea. Basically, what we're going to say is that there is that in the same way that when you take a vector space, then yes, you can work with an explicit basis and everything would be fine. But sometimes it's more mathematically insightful to work with the entire space at once. So just consider the vector space and not restrict yourselves to thinking of vector spaces as combinations of some specific basis vectors. So in this talk, what we're going to do is that we're going to take this idea that maybe the space of zeta integrals is more important than the single representative, which is the L function, and see if it, and we will find out that we can really get some interesting results out of this idea. So in this talk, what we will, maybe our main focus will be giving a nice proof for explaining why these two very different, or maybe even exploiting the fact that these two very different zeta integral formulas not only give the same L function, but in fact, they give the same space of zeta integrals. What this means is that we will have some way to associate zeta integrals of Godement-Jacquet type with zeta integrals of Jacquet-Langlands type. Essentially, we'll be able to take pairs of vectors and some additional data and compare it, associate it to just a single vector. So we'll have this kind of multiplicative structure, a new kind of operation, and this will give us an exotic multiplicative structure on both in the local p-adic case and in the global automorphic case of representations. So that's going to be the main focus of this talk, just to explain how to explain this equivalence and how to get consequences from it. I will say that all of what I'm going to tell is a part of my PhD thesis, which was done under the supervision of Joseph. And that's it for now. So let me very briefly go over the plan, and then we'll see if anyone has questions about what we're planning to do today. So there's an introduction, which I just gave. Then we'll straighten up, establish a ground level about periodic representation. We'll compare Godement-Jacquet and Jacquet-Langlands zeta integrals. We'll use that to construct this monoidal structure that I promised. Then I will apologize. And then I will show some applications to the global theory that I haven't had time to do when I last gave this talk, but hopefully this time we will have, which is how one can use this idea to discuss to construct a candidate for a category of automorphic representations. I will probably butcher this part because I'll hopefully give you a bit of a taste, something enough to be interesting, even if not to give you a whole lot of information about it. Any questions about the plan? Okay, so I'm not hearing any questions. So I'll assume that either I'm talking to myself or people have understood. Okay, so let's begin. So let's begin by establishing some notation. Let's start in the local periodic case. We have a local field of characteristic not 2, and we denote GL2F by G. We have a category of smooth G modules. This means that a smooth G module is a G module where every vector is fixed by some neighborhood of unity in the group. We also have a contragradient duality, which I'll denote by V tilde, which consists of the smooth covectors, the smooth linear functionals on my space. Finally, there's something that's called the generic, that would say that a G module is generic if it has what's called a Kirillov model or a Whittaker model sometimes. This is probably not enough for someone who doesn't know what any of this means to understand what it means, but for those who do, this is at least established, maybe will at least not get confused over terminology. So let me give a quick reminder about Godement-Jacquet functions and the Jacquet-Langlands L functions. Basically, how does a Godement-Jacquet function work? You start with a matrix coefficient, which is basically something that consists of a vector in my representation, a covector, and you just consider it as a function on the group by applying just by taking the corresponding matrix coefficient, just by applying the element of the group to the vector and multiplying by the covector. The next thing you need is a test function, which is a smooth compactly supported function on M to F. And then you integrate them together. You take the matrix coefficient, which is a function on GL to F. You take the test function, which you can restrict to GL to F. You integrate them with some function, and you get a meromorphic function of S. This is called the meromorphic. This is called the zeta integral. And when you take the GCD of all of these functions, then you get something called the local L function. Now, the second thing that we're going to discuss is the Jacquet-Langlands L functions. How do they work? You have a Kirillov model, which is essentially something that takes a vector in my space and associates to it a function on F. If it has to satisfy some properties, and if it exists, then it is unique up to scalar. You take a test vector inside your representation, and you integrate the resulting function. Just take this test vector, you turn it into a function on F via the Kirillov model, and you integrate it. This gets you a meromorphic function of S, and you can write that, and then you can use the GCD to get exactly the same L function as before. So it is known, there are many ways to show it, some of them more explicit than others, that when you do these two procedures, you get the same L function. We want a nice conceptual proof of that. So in order to do this, what we really want to do is we want to compare the spaces of zeta integrals. This means that we have to compare not just the zeta integrals, but we have to compare the data that goes into them. So we need to be able to explicitly state exactly what is the data that goes into defining a Jacquet-Langlands L function, and then associate to it explicitly what kind of data goes into the Jacquet-Langlands L function. Hopefully, when we write these pieces of data precisely, they will be the same somehow. So indeed, we have data, which is a covector, a vector, and a test function. Unfortunately, this combination has some redundancy. So if we go back, then we see that if we multiply v by h, then this corresponds to right translation of beta, which is the same as right translating psi, and similar with left translations. So this is actually with, so we don't, our input data is not just the tensor product of v and v tilde with this space of test functions, but it's a tensor product over G.
Can you just repeat the definition of Jacquet-Langlands L function? I missed it.
Yes, sure. The Jacquet-Langlands L function is defined as follows. If you have a generic representation, then it has a Kirillov model. If this Kirillov model exists, it's unique up to scalar. Basically, what a Kirillov model is, it doesn't really matter at this point. What it is just it's something that takes a vector in my representation and associates to it a function on F. We call this W, this pairing. So we take a test vector in V. We apply W to it, so we get WV, which is a function on F. This is basically the Whittaker function, and we integrate this function over F star.
Thank you.
So, as I said, the data for the Godement-Jacquet L functions is something in the tensor product over G of V times space of test functions times G times V tilde. But there's a very big if here, something that needs to be mentioned, which is that there's actually an overcounting of redundancy here. Because if we go back a bit, then when we integrated psi and beta, if we translate both psi and beta, this isn't actually equivalent to doing nothing because the determinant pops out. So basically, we're only allowed to shift we're only allowed to move copies of G from V into the test function and from V tilde into the test function if the product of their determinants is 1. So I can either invent some new notation for it, or I can just fix this overcounting by increasing the space of test functions. I can just say that this is, if I add here times F star, then, and I let G act on this space on the left, so I have the space of functions on M to F times F star. I let G act on it on the left by translation on M to F and determinant on F star, and from the right by translation on M to F and determinant on F star. And if I do this, then I get something that exactly accounts for all of my degrees of freedom correctly. It correctly accounts for redundancy. Now the space, so this is the data that goes into a Godement-Jacquet zeta integral, and the data that goes into Jacquet-Langlands zeta integrals is much simpler. G up to a Kirillov model, which is just a scalar, it's just a single vector V in my representation. So the space of Kirillov of Jacquet-Langlands zeta integrals is V. Now, here is basically the claim that we've ended up with. If we suppose that these two spaces should be isomorphic, then let's just go out and say it. So here is the claim that we are trying to prove, or that we are trying to consider, that that these two ways to index zeta integrals are actually the same. There is some correspondence between elements of V and pairs of vectors, covectors, and test functions. And that this isomorphism should respect zeta integrals. That is, that the zeta integral corresponding to the data on the right-hand side should be the Jacquet-Langlands zeta integral corresponding to the data on the right-hand side should be the same as the Godement-Jacquet zeta integral corresponding to the data on the left-hand side. This should be a canonical isomorphism fixed by this requirement up to the choice of the Kirillov model.
Sorry, a question. What about character? Or S in your notation?
No, this S basically is what gives me this F star here in the space of test functions. Yes,
and on the right?
And on the right, note that, so if I did this naively, yes, if I didn't put S here in the definition of the Jacquet-Langlands zeta integrals, then my space wouldn't be given by V, it would be given by V modulo F star, because I'm taking an integral, so it's invariant to translations. But I'm not doing that. I'm taking the entire function V because that exactly captures the data of its integral against all possible characters. So I'm taking the entire function WV of Y rather than applying some quotient of it.
Okay.
So yes, this.
Okay. Let's proceed.
Okay. Let's. Basically, it's not very easy. It's not very difficult to convince ourselves that if we take zeta integrals with all possible characters, then that's equivalent to just saying that this function here, WV of Y, is given by some function given by that can be extracted from this psi g and beta g, which is basically the map that we are constructing right now. So
the isomorphism is of vector spaces, or what's the claim exactly?
So right now it's a vector spaces, because as far as I've defined the left-hand side is just a mere vector space. It doesn't have an obvious G structure, but that's obviously wrong because the right-hand side does. So one of the things that the immediate next thing that I'm going to say is that this is in fact an isomorphism of G modules. But right now it's still an isomorphism of vector spaces. So I'll go back to that in a moment. That's an excellent question, as they are called. But in the meantime, you should note that this claim is one thing that's pretty remarkable about it is that it's non-linear in V. Yes, I have an isomorphism of vector spaces, but the left-hand side that I claim is canonical, but the left-hand side has 2 copies of V and the right-hand side has just 1. So something very weird is going on here. Hopefully it will be clear what is going on here by the end of the lecture. I intend to deliver an explanation. So first of all, as Erez said, something very weird happened here. I said that this space on the left-hand side, which is not a priori a G module, is isomorphic to a G module. So that means it should have some kind of G structure. So it's not clear where this should come from, because this space in the middle of test functions, functions on M2F times F star, it has an obvious left G action, an obvious right G action, but I've used both of them already. So I need to have some third G action that commutes with both in order to have a G action on this tensor product. And in fact, once I have this action, it turns out that the proof above is very easy. It's once you know that this space V tilde times Y times V that it actually carries a G action, then identifying exactly which specific G module it is not very difficult. So really the only hard part here is realizing that this should have a third action. And in fact, this action is not very difficult to construct. In fact, I'm going to just tell you what it is outright. So I'll do this by saying what Joseph told me when I told this situation to him, when I said that this space should have a third G action. He said that the only way you can have this many commuting operators is if the Weyl representation played some role here, and it turns out that it does. So let me be very brief here. I am not assuming that all of the audience is necessarily familiar with the metaplectic group or the Weyl representation. If you're not, then you can just, then it's fine to lose me during this single slide. We'll not go back to this. So just, this is just for so that I'm not being mysterious here. So just the construction is very simple. You just consider a 2-dimensional symplectic space. Let's call it U. Then you can consider U times U times U. That's a symplectic space as well, but just by taking the pairing on U times the pairing of U times the pairing of U. And the cube of GL2F embeds in here, or rather only the subgroup of determinant 1. Yes, if you have 3 matrices whose total determinant is 1, then they respect the metaplectic, the symplectic pairing on U times U times U. And what this means is that we have a Weyl representation that if we choose some Lagrangian inside this 8-dimensional space, then it's a 4-dimensional vector space. Let's call it M2F. Then this space of functions on M2F carries an action of GL2F cubed with determinant 1. And finally, I can use induction with compact support from this subgroup of determinant 1 to all of GL2F cubed. And I exactly get this, recover the space Y, this space of functions on M2F times F star, but this time with an explicit 3 actions of G that all act on it. Any questions? Okay. So that was the last thing I will say of metaplectic.
There were no questions just because it took us some time to unmute the mic.
Ah, yes.
Can you, again, I mean, it's sort of hard to see everything on one slide. Again, how do you view this as, can you just go over this again a bit once more, how you view this, how you identify between how you use this 3-tuple of GL2F matrices to say something about the smooth functions on M2F times F star?
If I have the space, so I have to consider the two-dimensional symplectic space, just F plus F. Then consider the tensor product of U times U times U. This has a natural action of GL2F cubed. Yes, one copy of G acts on the first coordinate, the second on the second coordinate, and the third on the third coordinate. Now, if I have tuples of 3 elements of GL2F that have total determinant 1, then they respect the symplectic pairing on U times U times U, because the action of each one of them on the symplectic pairing is just its determinant. So we get determinant of G1 times determinant of G2 times determinant of G3. So the subgroup of determinant 1 of GL2F cubed is embedded in the space of symplectic operators on U times U times U. Now, if you have a symplectic space and you have a Lagrangian subspace, a subspace where all vectors pair to 0, a maximal such subspace, then that subspace has what's called the Weyl representation. Basically, it turns out that there's a 2-cover of the symplectic group, which is called the metaplectic group, and this 2-cover acts on the space of on the space of compactly supported smooth functions on this Lagrangian. In this case, if we just consider the Lagrangian subspace U times E2, then we get this space of functions on U times U, which we identify with M2F. We have 2 copies of G acting on it, one with just by acting on the first coordinate, the second by acting on the second coordinate, and the third acts by some differential operators, by some more complicated operators, sorry. So basically we get an action of, we actually get an action not of the symplectic group, of the metaplectic group, but this embedding of GL2F cubed lifts to the cover, and you get an action of this subgroup GL2F cubed of determinant 1 on functions on 2x2 matrices. And now if I have a subgroup, then I can use compact induction to give me a representation of the entire group. And what this does to the space is that it multiplies it by functions on the quotient. In this case, the quotient group is F star. So I get functions on M2F times F star. And this is, it comes equipped with the structure of a G cubed representation. Okay, does this make sense?
That makes sense.
Okay, excellent. So just let me give a quick recap, just so we haven't lost anyone. What we've done so far is that we've made some accounting of what is exactly the space of zeta integrals, or how are the zeta integrals indexed, both for Godement-Jacquet and Jacquet-Langlands zeta integrals. We discovered that one such, the Godement-Jacquet zeta integrals are indexed by some data, including a test function and a covector and a vector, and the Jacquet-Langlands are indexed by single vectors. We decided that these 2 things must be isomorphic because we want the spaces of zeta integrals to be isomorphic. And we realized that this would mean that this space Y must have a third G action, and that once it, and in fact, my claim is, what I claimed to you just now is that once you associate it with this third action, then there is a canonical isomorphism of G modules between V times Y times V tilde and V. And moreover, that this isomorphism respects zeta integrals. So the Jacquet-Langlands zeta integral of the right-hand side is the same as the Godement-Jacquet zeta integral of the left-hand side. Okay.
So I have a question.
Florent, I had a question. So you say, maybe you will talk about this later, but so you said that this isomorphism is canonical, but it seems to me that that maybe I got it wrong, but it seems to me that you need this E2, this vector in U to define this. You needed the Lagrangian, right? So you use the choice.
So I can basically, this E2 is part of, you can say that this is something that comes from what's called the Whittaker datum. I haven't described it here. It's,
and this somehow is contractible or something.
It's some standard structure that you can associate to GL2F. I will, maybe not in this talk, but there was actually, I can also say what happens when you choose different Whittaker data, etc. But for GL2F.
Okay, so it's just a point that you deliberately did, but it's okay. It can be dealt with.
Yes, yes. This
So
is called
the situation is that the input for a Godement-Jacquet integral is something from the left-hand side, and to Jacquet-Langlands is something from V, and you're going to show isomorphism between the spaces and also between the respective integrals, right? Did I understand this?
This is what I claimed. I am not going to show this. I said what I said was that the proof is easy once you know that the left-hand side is also a G module, but I'm not going to show the proof.
Okay, but this is the truth that you want.
Yes, this is the state. This is my statement. Correct. Okay.
Can you just quickly explain the embedding again of GL2 cubed into this symplectic space?
Sure. It's not really important. So if I'll probably not. So I'll say it again, but I probably don't really want to dive into it any deeper. If you have U times U times U, then you can just act. You have an action of G cubed on U times U times U just by letting the first copy of G act on the first coordinate, the second on the second, and the third on the third. And what this does to the symplectic pairing is that this just multiplies it by the determinant of the matrix. So if I have a tuple of 3 matrices whose total determinant is 1, then they just happen to, they define a symplectic endomorphism.
So I'm a little bit confused about the dimensions here, because the U tensor 3 is going to be what, 8-dimensional, and you could view sitting inside GL2F SL2F, and that's going to be 3-dimensional, and 3 copies of that's going to be too high to be in here.
It's not embedded in U times U times U. It's embedded in the symplectic group of U times U times U. This symplectic group.
Okay. Sorry.
Okay. So let's maybe try to make sense of what happened here. We constructed this. We started with this problem of understanding zeta integrals, and we ended up with this strange trimodule. Yes, we have an object with 3 different commuting G actions. Now that's something that's very uncommon. Yes, you don't just walk off the street and see a trimodule. It's not something that, bimodules are things that you see all the time. You do math, you see bimodules, they're everywhere. But a trimodule is much more rare. So if you see something like that, it kind of begs for an explanation. So you really need to try to put it into a framework, because again, it's not something that you see every day. Now, fortunately, there is something that you can do to be able to think about this, which is, instead of thinking about this space Y as a bimodule, as a trimodule, let's instead think of it as a bifunctor. That is, if I have 2 G modules, V and V prime, I can just say, okay, take V times over G with Y times over G V prime, and let G act on the result via the third action on Y. So this defines a bifunctor from G modules and G modules into G modules. And unlike trimodules, which are strange objects that you never ever really see, bifunctors are very common. Just any kind of tensor operation or monoidal structure is naturally a bifunctor. So so now, of course, so we didn't construct this to be so a bifunctor is a much more natural object to think of, but just like you don't really expect any kind of bilinear operation that you randomly choose to be an associative algebra, neither is it reasonable to expect this to actually be a tensor product. Yes, it would be amazing if this happened. So amazing that it actually does. So here is a surprising thing that just pops out of thin air once you try to force this thing into making sense, is that this bifunctor that I defined, that taking pairs of representations and multiplying them via Y to get a third representation. In fact, not only is this a bifunctor, but it can be extended essentially uniquely, to a symmetric monoidal structure on the category of G modules. Now, what does this mean? This means that there's an object that's a unit for this structure. That is, there's a space that if you multiply it with Y, then you get the identity functor. There is this monoidal structure is symmetric. That's additional data. There's a natural isomorphism between it and its symmetric version, and it's associative, which means that there is some natural isomorphism of functors between the two ways to compose it with itself. All of this is extra data, and the combination of this data is actually turns out to be unique in this case. Just to avoid being mysterious, in fact, the unit is just what is usually called the Whittaker space. Basically, space of functions turns out to just be the space of functions that are equivariant with respect to a certain character. And this is amazing. This was the point. This is something that really shouldn't happen, and just straight up pops in here out of the blue. That it turns out that you have this symmetric monoidal structure. So any questions about what this means? Because people aren't really used to thinking about exotic symmetric monoidal structures. So probably this is a place where people have questions.
Will you define this structure and explain why the Whittaker model is the unit?
So defining a structure means defining all 4 pieces of data, which means the essentially which means the bifunctor, the unit, showing the natural isomorphism, showing that this multiplication with this unit is the identity, symmetry, and associativity. There's a lot of data. I'm not going to display, certainly not all of it. The bifunctor I've essentially given you. The fact that this unit is given by the Whittaker space is something that can be explicitly seen from just standard the ways from how the Weyl representation acts. I'm not going to tell that either. I can easily explain why it is symmetric. That's the simplest thing here to give. It just turns out that you don't only have an embedding of G cubed inside this symplectic space, but in fact you have a semi-direct product of S3 times G cubed acting on this, and that just immediately gives you symmetry. But I'm not, and the associativity, I have proof that it exists, but this proof is constructive, but not very. Or I can have something that's completely explicit computation, or I can have some explanation that shows what it is, why it is unique and must exist. But it's not something that I can give in a quick lecture, unfortunately.
I have a question which you can dismiss if it's too it's asking for details which you don't want to talk about. But when you say G modules, so could you be like a bit more precise? Like what kind of G modules?
So for me, a G module is a smooth representation of G, just smooth G modules.
Oh, okay, great, thanks.
Just as we defined in the beginning.
Great.
So now this already gives us some hint of so basically using this language of the symmetric monoidal structure, it really hints that what we were doing earlier about saying this that this strange isomorphism between V and V tensor Y tensor V, that there's something a bit more interesting to it maybe. Let me just so in fact we can now reformulate this earlier statement in much nicer terms now that we have this. We know that this is a monoidal structure. Before I do that, I need to make one last comment. Recall that this Whittaker space, the unit for my monoidal structure, has the property that it has a multiplicity 1 property. That the dimension of the home space between it and any reducible representation is either 0 or 1, and it is 1 exactly when the representation is generic. In fact, the data of choosing a map from 1 to V is precisely the same data as choosing a Kirillov model, which is the data that we used earlier. Now, in fact, this exactly tells us what the isomorphism that I described earlier was. So just in any symmetric monoidal category, you have the following construction. If you have you have the tensor product of V with the space of maps from 1 to V, this is just isomorphic to V times 1 times this space of maps. And this has a canonical pairing into V times V. This happens in all symmetric monoidal categories. You always have this map. And it turns out that the earlier map that we had between V and V times V was precisely the inverse of this map. And in fact, what we're saying is that when V is a generic irreducible representation, then this map is an isomorphism. And it respects zeta integrals for some reason. But this turns out to be precisely the map that I described earlier. So in fact, this is, as I stated it right now, it's not even very difficult to prove. It's much easier to prove than it was when I stated it earlier. Because you have, because this, suppose that V is a generic irreducible representation, then the map between 1 and V, between the Whittaker space and V, is surjective. It's easy to show because it's irreducible, and it has such a map because it's generic. But it turns out that it's a general property of symmetric monoidal categories, where the symmetric monoidal structure is of a billion categories, which are symmetric monoidal, and the symmetric monoidal structure is right exact, that if you have a quotient of the unit object, then that quotient is a commutative idempotent algebra, that it exactly has this property that V times hom from 1 to V is isomorphic to V times V, and that it's in fact a commutative associative algebra. So in other words, not only do we have that this isomorphism that I described earlier, that showed us that Godement-Jacquet and Jacquet-Langlands zeta integrals are the same, not only follows from abstract nonsense, but in fact it defines a bilinear operation, and that bilinear operation is associative, which is really, really nice. So now this is pretty bizarre. Yes, it's not something that you come out expecting, but maybe let me give something that will give an interesting perspective on it, or maybe give some intuition. So let me maybe say a few words about generic intuition here. If you have just any group G, doesn't have to be GL2F, just doesn't have to be anything, then you have a product of G modules just by taking diagonal action. Yes, if I have two G modules, I can take V times of V prime, not over anything, and this has a diagonal action. But this action plays very badly with the spectral decomposition. Yes, if V and V prime are irreducibles, then V tens of V prime can be pretty complicated. It doesn't have to be, it doesn't have to have finite length. It can be pretty terrible. However, if my group is commutative, then I have a much nicer symmetric monoidal structure, which is the relative tensor product. If I have two G modules, I can take the relative product over G. And because G is commutative, this product will also carry a G module action, G action. And unlike the non-commutative case, this relative tensor product respects representations being irreducible. Yes, if I take two irreducible representations and I tensor them, then because the group is commutative, then they're all one-dimensional. So if I tensor them together, I either get 0 if they're different representations, or I get just the same one. So every irreducible representation has this property that V times V is V. And this behaves much like our new construction. This exotic symmetric monoidal structure acts very much like the second case, even though GL2F is not really commutative. So basically, a key property here is that somehow, and this is something that I can show several examples of, it turns out that if you consider the category of GL2F modules armed with this symmetric monoidal structure Y, then it behaves very much like you would expect from a commutative group with its relative tensor product, even though that doesn't exist here, even though the group is not commutative. So this is basically...
Guys, there is some commutativity here. It is the diagonal G is a Gelfand subgroup in the triple product. Mm-hmm. So is this the commutativity?
So in my experience, when you have, I think, so Gelfand subgroups correspond to algebras with respect to this monoidal structure. I can discuss this more deeply, but basically, it turns out that, for example, you have all kinds of structures. For example, you have a parabolic induction from the diagonal subgroup here, and it turns out that for example, this diagonal structure, this parabolic induction is right lax. It respects the symmetric monoidal structure, and that's essentially a property that it's a manifestation of this multiplicity one property, of this Gelfand property. So it's related. I'm not sure that I can say that it follows from.
My guess would be that it's related to the commutativity of Y, of the Whittaker space, yes?
Yes. So this is another element. This is actually something that I use in my proof, that there is this extension that, so I cannot consider this a proof that Y is commutative, but in retrospect, if you only knew this statement and you didn't know that Whittaker spaces had multiplicity 1, then you could deduce it. Yes, because it's very easy. It's very well known that if you have the unit in a symmetric monoidal category, then its endomorphism object is the commutative algebra. So you can immediately see that.
Okay.
You
So,
have
so
this,
it's included in at least, yes.
yes, it's at least included in this theory. I cannot say that this is the proof because I had to use essentially the same argument in order to deduce this symmetric monoidal structure. But this is definitely absolutely related. Yes. Any further questions before I proceed to apologizing?
So do I understand correctly? You didn't say anything about how this formalism relates to L functions yet.
Not directly. In fact, the whole point I'm trying to make is that the L function itself, that you really shouldn't be not that you shouldn't, but that it's very interesting not to consider the L function itself, but rather the space of zeta integrals. And that,
okay, but to zeta integrals, you also didn't tell.
No. So basically, my claim is that there are two ways to associate the zeta integral to a representation V, and in fact, I said that I reformulated them in this theory, in the language of this theory. I said essentially I said that the Godement-Jacquet zeta integral is not something about test functions and matrix coefficients. It's just a vector in V times V with respect to this exotic monoidal structure, and that the Jacquet-Langlands zeta integral is not indexed by elements of V, but simply by, or it's simply indexed by elements of V times maps from 1 to V, or elements of V equipped with a Whittaker model. And I said that there's a canonical way to identify these two spaces of zeta integrals.
Okay.
So I probably missed it. You probably said it before. So Vy times V is just this triple product of V times as a space, not as a functor, but just as an object. It's V times S of mat times F.
Yes, this is the definition of the circle Y. It's just the bifunctor that you get by taking this trimodule Y and pairing two of its entries with your vectors and letting the third hang free.
Y is trimodule.
Yes, Y is the trimodule is it's this space of functions on M to F times F star.
And what is the triple action? You probably said it. I'm sorry, I just
it's construction that involved the Weyl representation. It was
okay.
not very complicated in its construction.
But okay, you don't have to say it again. Yes, sorry.
Okay. Any further questions?
But this, yeah, maybe I didn't understand, but this kind of doesn't talk about, say, analytic properties of
no, I don't know to say anything analytic. This is not
just about the data that parameterizes the zeta integrals, kind of.
Yes, I'm talking about algebraically about the space of zeta integrals rather than their manifestation as analytic functions. I do have some description of that appears in my thesis, but not in this talk.
Okay, thanks.
But I do have some way to translate these spaces into their manifestation as actual analytic functions. That's very interesting by itself, but it's not for this talk.
So if you have a representation which is not generic, like say irreducible representation, so this triple product just this Y product just kill it?
No, so I can tell you exactly what it is. There's essentially only one irreducible representation that isn't generic in the case of GL2F. That's the trivial representation, or just any one-dimensional character. And what happens when you take the one-dimensional character and you multiply it with itself? Then you don't get an irreducible representation as a result. You get an extension of a Steinberg representation with this irreducible character. So you get a reducible representation.
You took now the product of a character with arbitrary representation or with itself?
No, with itself.
And with arbitrary?
So
okay,
if they have different central characters, then
everything die.
If you multiply it with the Steinberg representation, then you get 0 as well. And if you multiply it with itself, you get something non-trivial. But you also get something non-trivial if you multiply it with the length 2 extension of a Steinberg with itself. There are two extensions, two ways to construct a length 2 representation from them. And you get different things depending on what order you multiply, on which one you multiply.
It's not exact.
It's right exact, but not left.
So I can get some partial guess, but not what I need to know more, I think.
Mm-hmm. Okay. So now I think this is the point in time where I apologize. So I have 15 minutes left, and I would like to tell you some interesting things about the global theory. Now, unfortunately, the things I really want to tell you about the global theory are basically their own lecture, so I won't do that. I won't do that well. Instead, I'll just give you some teasers and give you, I'll say interesting things and have to remain mysterious about the details. The contents are, I plan to make them available, the exact details available as soon as I can. But so I apologize in advance. But the next thing I'm going to do now is to describe what happens when you try to apply this to the global theory, to automorphic representations rather than periodic representations. So first of all, let's introduce some notation. We have some global function field of characteristic not 2. I'm choosing a function field because I don't want to deal with Archimedean places and things like that. Let's just keep things simple for now. We have the Adels A and we have GL2A, which we call G. Now we also have a category of smooth G modules called mod G. But unfortunately, unlike the local case, in the global case, the category of smooth G modules is huge. It has a lot of things which are utterly irrelevant to the theory of automorphic representations. Yes, out of this huge category that corresponds of any way to fit local representations into global ones, there are only very few representations that are actually interesting, that are called automorphic representations. Now, you can ask me, Gal, why don't you just study the category of automorphic representations? And the answer is that it's not really clear how to define that. You can say that an irreducible representation is automorphic. That's something that makes sense. You ask if it can be embedded in some space of functions on the automorphic quotient, and that tells you if in irreducible, not if it can be embedded, if it's a subquotient of a space of functions, but that's really something that only makes sense for irreducible representations. It doesn't make any kind of sense more generally. So it's not really clear how this automorphic representations might fit into a category. And what I'm going to do now is that I'm going to in a very undetailed way, just give you just an explanation of how this might be done, or to give you a candidate for a category of automorphic representations. So just let's bring the theory that I described earlier to the global setting so that I can do this. We have the space of functions m to f times f star earlier. But it turns out that there's nothing special to the local circumstances there. You can just use the same exact construction for the Adels, and you end up with with an Adelic space, the functions on m to a times a star. And this space turns out to have a triple G action of an action of GA times GA times GA. And you can use this to define a symmetric monoidal structure, just like in the local case, whose unit is the Whittaker space, which I denote by the same notation 1y, and this is a symmetric monoidal structure which is given by v tensor over g with this space tensor over g with v prime. So just believe me when I say that you can show that the local statement implies the global one, that you also have a symmetric monoidal structure in the global case. Now, let me maybe introduce one more piece of notation. Consider the automorphic quotient, functions on GL2A modulo GL2F, and consider not all functions there, but those that are orthogonal to all characters, to all functions of the form chi of that G. So we have smooth compactly supported functions that are orthogonal to characters. You can think of this as being generic automorphic functions. This is also the image of the Whittaker space inside the space of automorphic functions.
Can I ask something? Throughout, when you say compactly supported, should I think of possibility of having Archimedean places and Schwarz functions, or do you really mean compactly supported?
So for now, I'm not describing. I'm deliberately using function fields in order to avoid thinking about this. But you should be able to consider Schwarz functions and fit them into this theory. I just have not done the legwork to be able to say this. That what happens exactly. So you have this space of compactly supported functions that are orthogonal to all characters. Now the thing is that when I described locally this construction, when I constructed the triple action on this space of functions on m to a times a star, then I used the well representation. This is a part of a theory called the theory of theta correspondences. Now the theory of theta correspondences is something that's very important and big in automorphic representations, and it has two components. One component is called the theta is the theta correspondence itself. It's some functorial construction that allows you to take representations over one group and turned into representations on another group. Now, the second component of this mechanism is something called the theta functional. It's something that doesn't always work, but when it does, it shows that the result of the previous construction is itself automorphic. And that's very important because we want to be able to, because the Langlands program is all about taking relating automorphic representations for various groups. So in this case, when you try to work out what this second part of the theory of theta correspondences means, what this theta functional actually turns out to be in this setting, when applied to this specific well representation, then it turns out that it just turns out to straight up define a map from, let's call this, from this space I times I into itself. Just a bilinear map from generic automorphic functions to generic automorphic functions. This turns out to be the entire content of the information that's contained in that theta functional. I'm not going to walk you through it, but it's, again, because due to lack of time, and I apologize for that because it's very nice. But
can I just ask? Maybe I missed. So here you mean by this product that you still have a product on the whole category of adelic representations? So
yes. Just as you can see here, just to take the same exact local construction using the well representation, just works in the global case, and you can associate the space of functions on M to A times A star with a G times G times G action. This time adelic G times G times G. And you can use it to define a bifunctor, which turns out to be a part of a symmetric monoidal structure whose unit is the Whittaker space.
Okay, thanks.
Yeah,
do you mean the Whittaker space corresponds to the principal character, which is trivial on the on F?
Yes.
This is what you mean. Okay.
Yes.
So this is a piece of purely automorphic data.
Yes.
Not the adelic data glued out of the local data.
No, sorry, maybe I'm confused. Can you say? No. The Whittaker space is the space of functions on GL to A, which is equivalent with respect to some character on the unipotent subgroup.
Which is trivial on the rational ones.
Yes, it's trivial on the rational one, but this model is still equal to a product of local modules.
Sure, absolutely. But this piece is something global.
Yes.
Because you could have taken something which is not trivial on the principal adels.
Yes. It's in fact
okay.
I can do it for any character, even non-principal ones, but then I wouldn't get this phenomenon. I wouldn't.
Sure. No, I understand. Yeah, okay.
So I get this bilinear structure, but not with respect to the usual monoidal structure, but with respect to this Y. And by now, it shouldn't be surprising that this theta function, this bilinear operation that comes out of the theory of the theta correspondence turns out to make I into a commutative algebra with respect to this monoidal structure. So basically, there's this map from I times I to I, and this map turns out to be commutative, but associative, have a unit, and everything else you can expect from an algebra. Only instead of being with respect to the usual tensor product of vector spaces, this time it's with respect to this symmetric monoidal structure Y. So what does this? So first of all, this is really nice. I have an algebra of automorphic forms, yay! But more than that, there's something that's pretty much asks itself, which is if you have an algebra, you can ask what are its modules. So if you have an algebra in the symmetric monoidal category, then you can consider its category of modules. In this case, there are G modules that are equipped with a map from I times M to M, such that this map satisfies the usual axioms that you want out of a module. This turns out to be a category, which I'm going to call for the rest of this talk the category of abstractly automorphic representations. And for now, this category is going to be my answer to the question: what is the category of automorphic representations? What is an automorphic representation? Now, first of all, something that people might object to is that being a module is usually in some piece of extra data. It's extra structure. Yes, basically, when I'm telling you that an I module is an automorphic representation, it seems as if I'm saying that a G module is not in and of itself an I module, an automorphic representation, but only when you add some extra piece of data. But as it turns out, in this case, this is not actually the case. it turns out that the forgetful functor that takes an I module and just forgets the I module structure is in this case fully faithful. So what this means is that being abstractly automorphic, being an I module is a property of a representation rather than a piece of data. So even though it looks like something that you need some extra data for, that you need to define an action of I, it turns out that if I has an action on a G module, then that action is unique. So being abstractly automorphic is a property. Essentially, this means that this category, mod auth G, can be thought of as a fully faithful subcategory of the category of mod G. So you have this huge category mod G that contains a lot of representations that are completely irrelevant to automorphic representation theory. And inside it, you have this category of I modules, which, as it turns out, is much, much nicer to work with. So let me just throw some properties at you. I'm not going to say nearly all of them.
Will identity trivial representation belong to this category?
Yes. In fact, for an irreducible representation, if it appears as a subquotient of space of automorphic functions, if it's automorphic in the usual sense, then it is also abstractly automorphic.
Maybe it's not relevant here, but can abstractly automorphic be somehow related to the more naive thing of having some map to the space of automorphic functions?
So even so let me give some. So it turns out that there are irreducible representations that are automorphic in the sense that they are subquotients, but they can be strict subquotients. So for example, for example, if they're called anomalous automorphic representations. They come up in Eisenstein theory, but it turns out that you have automorphic representations that cannot be either a quotient or a submodule of the space of automorphic functions or its dual or anything of the sort. But they are still considered automorphic. They are still subquotients of it. And so, and they are also abstractly automorphic by this definition, but they don't have a map. So maybe let me give a few other examples. So a lot of spaces that, so for irreducible representations, this definition is well behaved. It coincides with the usual one, but it also makes sense for non-irreducible representations. So for example, the space of automorphic functions itself turns out to be abstractly automorphic. This space I is a module over itself, obviously, so it's abstractly automorphic. And in fact, this has also excellent closure properties. It is closed under limits, co-limits, subquotients, contragradients, any categorical operation that you can think of, they're closed under it. So for example, since we know that space of automorphic functions is abstractly automorphic, then this immediately implies that its contragradient is abstractly automorphic, and that all subquotients of it are abstractly automorphic.
Sorry, can I ask something?
Sure.
That so, and from this example, it seems that the space of abstractly automorphics are somewhat a bigger concept than the automorphic. I mean, and also even so, and as what you said, they're not. So there's no map to the space that you showed in your example. So what bad thing can possibly happen?
What?
So what bad thing can possibly happen, to make it so not to make the a map to the space in the example not existing?
So that's something that's pretty classical. So let me give just an example. Consider that consider the representation to consider the character. Consider the diagonal subgroup inside GL2, and so this has a consider a character of it, which is given by trivial on one coordinate and absolute value on the other coordinate. Now, when you do the parabolic induction from this representation, from this character into GL2A, then you get this representation which is infinitely reducible. At every place, you get something that looks like an extension of a Steinberg representation and a trivial representation. So you have this infinitely reducible representation. Now, this construction appears in the theory of Eisenstein series. By the theory of Eisenstein series, this kind of infinitely reducible representation appears inside automorphic representations. But unfortunately, it has this one-dimensional quotient, which you just take one-dimensional quotient at every single place, and it has this. But it also has non-trivial extensions of it. You can choose, like, in some places to have the Steinberg representation, and in some places to have the trivial representation. And then this is just a subquotient of it, which is not a quotient and not a subrepresentation. And this just happens in the classical theory as well. Unfortunately, the theory, this description would have been much nicer had these things not existed, but unfortunately they do. But I disclaim all responsibility. They are not my fault.
I have a question, a follow-up question. So one question is it closed under extension also?
Not, I don't think so.
Okay.
No, it's not. It's absolutely not closed under extension.
It's not closed under extension. Great.
I can show that.
Excellent. So because otherwise it was really weird. Now the next question is: does tensoring with is tensoring with I exact, like tensoring with respect to this?
So it's right exact, but not left exact.
It's right exact. Okay.
Right exact. It's
always right exact, but I was asking whether, but it's not. You're saying
it's not left exact. Absolutely not. Just even the easiest way to see that neither of these things is true is just that this has just a quotient of the center. Yes. The mod G has a huge center, but the category of automorphic representations has a much tamer center. And you take the quotient of the center in this way. And so because for quotients of rings, this doesn't happen, and this won't happen in our category as well. So again, this is just a very, very skin deep description, but it's just something that happens that I really wanted to say. But that's all I really wanted to say at this point. So if you have any further questions, please ask.
I do have a question. Oh. I do have a question. So how much of it is really GL2 and how much you expect to go to higher rank?
So that's a really good question. So first of all, I do not expect that for groups that are not GLN, I expect much stranger things to happen. I don't expect the category of G modules in general to be a symmetric monoidal category. Rather, I expect there to be some kind of operations that relate different groups together. Even just for quaternion algebras for GL2, you can see this. For inert forms of GL2, you can see that the category of modules, there is an operation there, but this operation is not from modules of the inner group to itself, but rather you can have, but rather it takes something from the inner form and something from the inner form to GL2. It's more complicated.
But what about quasi-split groups?
Sorry?
What about quasi-split groups? You don't expect it to be symmetric monoidal?
I think not, but I don't really have enough examples. I don't have any examples, basically.
But what about GL3?
So for GL3, I expect this to happen. In fact, this is something that I'm working on right now, to having a construction, because the well representation construction that I showed you earlier absolutely does not work. But I'm hoping to have a construction and proof in the GL3 case as well.
So you don't believe that you essentially have to use the fact, this triality, that GL2 is diagonally inside GL2 times GL2 times GL2 is Gelfand pair?
I think that this is not unique to GL2, that there is a similar construction that's going to happen in GL3. This is fate. It's not something that that I have proof of yet, but this is just something that I believe and I am working towards. In general, I think that there should be a construction for GL3, but it will be more complicated.
But as is, like tensor, like monoidal structure?
Yes, monoidal structure, symmetric monoidal structure for GL3. This is something that I think can happen. I can show some shadows of it. I can explain what I mean.
next question, you said that you basically come up with some good candidate for the category of automorphic representations.
Yes.
So irreducible representation is automorphic, more or less, if only if, or you say not exactly, but still, if it can be like embedded or sits inside the automorphic space, which is basically functions on quotients, G of A, modular subgroup.
Yes.
So if we go to some local analog, so we have group G and subgroup H, let's say symmetric subgroup, spherical subgroup, whatever. Do you have some candidate for the notion of category of distinguished representations?
Yes, I do. Only in the case of GL2 times GL2. So you have the modules of GL2 times GL2, and you have inside it the diagonal action of GL2. And so you can ask, is there's also something that very closely mirrors the global theory, the representations that somehow sit inside functions on G as G times G modules somehow mirror the global theory.
So here my guess would be just representations of G, no? So it's a wrong guess?
So the category is a bit more complicated, but it's very close to that. It turns out that, at least in the local case, it's something that ends up being determined by the action of the center. But there's a similar. You can define everything there. You have the symmetric model structure. You can turn functions on G, which is the analog of the, which is the analog of this space of functions. You can turn it into an algebra. It has a category of modules, and this category of modules is fully faithfully embedded inside G times G modules. And this gives you a category of distinguished representations that has all of these properties. That its irreducible representations are inside. That the irreducible representations are inside it, if and only if they are distinguished, etc., etc., etc.
And one last small question. You probably said, you of course said that I missed. Can you just repeat the definition of I?
Yes, of course. I is the space of functions that are compactly supported on the automorphic quotient, GL2A modulo GL2F, such that they are orthogonal to all characters. That if you integrate it over the space of things of determinant 1, then you get 0.
So subquotient of I are not all of automorphic representation, but some part of it?
Sorry?
So how should I think? So subquotients of I.
You shouldn't think of subquotient of I. So automorphic representations are subquotient of the big space of functions. That's what you should think of. I is an algebra. Its modules are the interesting thing, not its subquotients.
But its subquotients are not just some very special automorphic representation, or
the subquotients of I, for example, I think they do not include I'm not sure if they include. I think they don't include, for example, the trivial representation, and the trivial representation is automorphic.
So how should I think about this condition of being orthogonal to chi of determinant?
I think you should think of it as being generic, as having as coming from a Whittaker function. There's a natural map from functions on GL2 to GL2 modulo GL2F to the Whittaker space just by taking any function to its.
You took out all the characters, yes?
Yes, I took out all the characters.
So you take all the automorphic space, so that includes all the automorphic representations, then you erase out of it all the character, and this is I.
Yes. You take the things that have a non-trivial.
Yes, now I see. Okay.
Gal, can I ask about the fully faithfulness?
Yes.
Should I think of it somehow as accident related somehow to multiplicity 1? Or?
So there are several ways to think of it. I think the easiest, first of all, this is actually something that I can very easily say why it happens. This I, as I just mentioned, it turns out it's the image of the Whittaker space inside this space of automorphic functions. So it's a quotient of the Whittaker space, the unit of the symmetric monoidal structure. And it turns out that if you have a quotient of the unit object in any symmetric monoidal structure, then the modules are fully faithful. If you're in a billion category and everything is right exact, etc., etc., etc. So under very wide circumstances, this is just a consequence of the fact that I'm taking a look at a quotient of Whittaker function. So basically, the fact that everything has a Whittaker function is fully faithful.
Thank you.
Gal, can you say something about L functions and zeta integrals? What are your local and global zeta integrals in this setting?
Okay. There's something. There are things that I can say. I think they would be a bit too far off. There are things that I want to say, but I think they won't. They don't fit into what I have been. I think this saying much more. So I can say a few words, but a lot of it would be off topic, I think. I can answer this later if you want. Just.
I wanted to ask essentially the same thing. You mentioned that you have extension of this theory, at least partially, for GL2 cross GL2.
Yes.
And what is that integrals?
You're asking. No. I have an extension of the symmetric monoidal structure, not of the theory of Z integrals.
And do you know what Z integrals should be covered by this, or related to?
I can. I haven't really thought about this. I can think about this and I can try to give you nothing off the cuff.
Because I guess we know the Rankin-Selberg, but integrals in this case.
I don't think that this is what you'll get. After all, the local case that I'm describing is the case of distinguished representations, of representations that are essentially that appear inside functions on G. Yes, so you won't get Rankin-Selberg functions out of it, which involve two very different representations. This is the wrong theory to describe Rankin-Selberg Z functions.
But you do have a module which is the module of functions on the Rankin-Selberg variety, like the two-dimensional vector space induced up to GL2 cross GL2 from the diagonal.
I'm not sure. I'm not sure that I understand, but maybe we can talk about this later.
Okay.
Is the category of the abstractly automorphic representations closed under your tensor product?
Yes, it's a category of modules, and in particular, it's closed under the tensor product.
So could you say like what that product is doing on the Galois side?
So actually, I hadn't realized this myself, but I've actually been told what this should be. I think Yanis told Joseph, and Joseph told me. So basically, it turns out that there's this kind of thing where you have the geometric Langlands correspondence that relates sheaves on the space of local systems with D modules or adelic sheaves on the space of G bundles. So I'm defining something that's a product in the case of G bundles, and it turns out that, but very naturally, this space of O modules of sheaves on local systems, it has just a symmetric monoidal product that by itself, yes, that just as being sheaves on a space. And it turns out, and it seems like this is the same product. In the Galois side, this should correspond to relative tensor product of modules on local systems. So the trivial module should be the Whittaker space, and that's the unit in my case. But that's all I know. I haven't really thought about it. As I said, this is something that Yanis told Joseph, who told me.
Thanks.
Okay, thank you very much, Gal. Are there any further questions? Okay.
Can I ask, like, so are all of these tensor products like integral operators?
Sorry, can you
like
say?
are all of these tensor products like integral operators that you just like the Jacquet case that you defined before? Like, are they integral operators or?
yes, so the multiplication on I is actually very simple to describe. As I said, it is given by some theta functional. In fact, it's just a theta function. Yes, you have, it's an integral operator that takes functions on the automorphic quotient. It's that takes two pairs of functions on the automorphic quotients to a third function, and it is given by some integral against a theta function.
Nice.
Okay. Thanks everyone for coming. Thank you, Gal, for the wonderful talk. So next week we continue in the usual time, on the usual day on Wednesday, and Steve Miller will be talking. We'll send an abstract soon, and I already put an abstract in the Google Calendar. We'll be talking about unitary representations. Okay. Thank you again.
See you.
Thank you all.